Okay, guys, our lesson today is over the second fundamental theorem of calculus and the average value formula. I'm going to work a couple of examples here so that we can hopefully discover the formula for the second fundamental theorem of calculus. So this says the derivative with respect to x of the integral from 1 to x of t squared dt. So I'm going to let the d over dx just sort of stay in the front to begin this problem, and I'm going to focus just on the integral part. So if I take the antiderivative of t squared, that would be 1/3 t cubed evaluated from 1 to x. Continuing with the first fundamental theorem of calculus, this would equal to, plugging in my upper bound, 1/3 of x cubed minus 1/3. And then finally, taking the derivative of that bracket, I would wind up with x squared. Now for the second example, I'm going to do the exact same thing. So I'm taking the derivative of an integral, and so this will be the derivative with respect to x. To find this integral, I need to find an antiderivative of cosine t, so that would be sine t, evaluated from pi over 6 to x. And so plugging in my upper bound would give me sine x, subtract, and plug in my lower bound, sine of pi over 6 is 1/2. And the derivative of that parentheses then is cosine of x. So looking at these two examples, if I take the derivative of an integral, that's when I use the second fundamental theorem of calculus. And the first step of using this theorem is that I take the upper bound. Hopefully you're noticing here that really all that happened to get from this original problem here is that we took the upper bound x and we substituted it in for t, and that gave us the answer cosine of x. The exact same thing happened in example 1. We had t squared, and we took our upper bound x. We replaced t with x, and that led us to the answer x squared. So for the second fundamental theorem of calculus, step 1 is to replace t with the upper bound, which in this case is x. And so the derivative with respect to x of the integral from a to x of f of t dt is just equal to f of x. And what I want to point out real quick is that this lower bound a, which was a constant, didn't matter. It didn't matter what the constant was, just as long as it was a constant. And so if I'm taking the derivative of an integral, step 1 is to take the upper bound and replace t with that upper bound. Okay, on the next example, I notice that the variable bound this time is the lower bound, and that's not okay. We need that to actually be the upper bound in order to effectively use the second fundamental theorem of calculus. So we recall the properties of definite integrals that allow us to change the bounds. It basically just means that we apply a negative to the integral, and so the answer here is going to be negative, and then I'm going to do exactly what we did before, which is replace t with that variable bound, and so I'm going to get negative x squared. So if that bound, that variable bound, is the lower bound, then the derivative of that integral is going to have to be the opposite, or the negative, of f of x. Now, for the second example on this page, I noticed that the upper bound this time is not just x. The upper bound is now a function of x, in this case x squared, and so I need to see how this is going to change the process of using second fundamental theorem of calculus. We already know that the first step is going to be replace t with x squared, but the fact that it's now x squared instead of just x is going to give us a second step for using the second fundamental theorem of calculus. So let's see if we can discover what that is through examples. So I'm going to let the derivative just sort of hang out in the front like we did before. And using the first fundamental theorem of calculus, I need an antiderivative of cosine t, which would be sine t. And I'm going to evaluate that from pi over 6 until x squared. Continuing with the first fundamental theorem of calculus, I'm going to plug in the upper bound for t, so that's going to be sine of x squared, and then subtract and plug in the lower bound, and sine of pi over 6 would be 1/2. And now taking the derivative of this particular expression using the chain rule, because now I see that x squared is inside of sine x, the derivative of that is going to be cosine of the inside, x squared, multiplied by the derivative of that inside, which is 2x. And so what I'm noticing here is that this cosine of x squared piece right here, that is that first step that we've been talking about. That is the replacing t with the upper bound. Notice that the upper bound here was x squared, and we just replaced that t with the x squared. This next part, 2x, represents the derivative of that upper bound. The derivative of x squared is 2x. And so that means that the second step for using second fundamental theorem of calculus is to multiply by the derivative of the upper bound. And so let's see if we can generalize that using the formula in our box here. The derivative with respect to x of the integral from a to g of x, where g of x could be any function of x squared, x cubed, square root of x, it doesn't really matter, of f of t dt is going to equal to, step 1 is to replace t with the upper bound. So that would be f of g of x, just replacing the t in the problem, in the function, with the upper bound, g of x. And then step 2 is to multiply by the derivative of the upper bound, which we will call g prime of x. Okay, so now that we know the steps for using the second fundamental theorem of calculus, and hopefully have a good idea of when to use the second fundamental theorem of calculus, namely if I'm taking the derivative of an integral, now let's try to work some examples. So in letter A, we have that the derivative with respect to x of the integral from 3 to x of the square root of 1 plus t squared dt. So step 1 to take this derivative is to replace the t in this problem with the upper bound. So that's going to be square root of 1 plus x squared. Step 2 would be to multiply by the derivative of the upper bound. And if you look at the upper bound is just x, and so the derivative of that would be just 1. And so my answer would just be the square root of 1 plus x squared. Okay, I just want to point out something just real quick before we move on to the second example. Another way that the AP exam likes to sort of phrase these problems, very similar to what you see in A, is they might say something like, let f of x equal the integral from 3 to x of the square root of 1 plus t squared dt, and then find f prime of x. And so what this problem is essentially doing is it's giving you a function f of x that's defined as an integral, and it's asking you to find the derivative of that function that is an integral. And so if I'm trying to find the derivative of an integral, that is when I use this second fundamental theorem of calculus. So I want to make sure that that's really clear, that to use the second fundamental theorem of calculus, I'm going to try to erase that and not scratch it out, but actually highlight it, which is what I meant to do, not scratch it out. So good, it is going to actually let me erase, and so I'm going to highlight it. Second fundamental theorem is whenever I take the derivative of an integral. Okay, moving on to example B, we have the derivative with respect to x of the integral from 2 to x of this tangent of t cubed. And so once again, step 1 is I'm going to replace the t in that function with the upper bound, x cubed, or just x, and so it becomes cubed because there was already a cube in the problem, and then multiply by the derivative of the upper bound. And since the derivative of since the upper bound is x, then the derivative of that would just be 1. And so my answer here would be tangent of x cubed. That would be the derivative of that integral. For letter C, I noticed that the upper bound is not just x, the upper bound is x cubed. And so I'm going to have a multiplication by the derivative of x cubed at the end of the problem. So once again, step 1 is to replace t with x cubed, so 1 over 1 plus x cubed, and then multiply by the derivative of x cubed, which would be 3x squared. And so the result here would be 3x squared over 1 plus x cubed. Okay, so hopefully you're getting the hang of that. Replace t with the upper bound, multiply by the derivative of the upper bound. So in letter D, we have the derivative with respect to x of the integral from 2 to the sine of x of the cube root of 1 plus t squared dt. So step 1 is I'm going to take that function cube root of 1 plus t squared, but instead of t, I'm going to write sine of x. So sine squared of x, and then multiply by the derivative of sine of x, which is going to give me cosine of x. Now, real quick before we move on, I want to sort of just add an example e here, and I want to say, okay, what if g of x was the integral from, let's just say, 0 to x of f of t dt? The AP exam loves to give examples of functions like this. And so if this were the function g of x, then the derivative of g, which is g prime of x, would equal to, well, again, we would be using second fundamental theorem of calculus because I'm trying to take the derivative of an integral. And so I would take this upper bound, which is x, and I would replace it where that t is. And so that would give me just f of x. And so what I hope is that whenever you see an integral or a function of this form, that you actually notice just sort of right off the bat that the derivative of that is just going to be f of x. Okay, so we'll take a look at our first example here that involves a function defined as an integral. So the graph of the function f is given in this problem, and it's also told to us that the function g of x is the integral from 0 to x of f of t dt. So I notice over here that this is the graph of f, and the first thing that this problem wants me to find are several values of the function of g of x. So starting with g of 0, g of 0 just means to plug 0 in for x into that function, so that would be the integral from 0 to 0 of f of t dt. And by the properties of definite integrals, if my bounds are the same, then that integral must equal to 0. For the second question here, g of negative 1, that's going to be the integral from 0 to negative 1 of f of t dt. And so in order to find this integral, we were given the graph of f so that we might find the area under the graph of f from 0 to negative 1. So from 0 to negative 1, that would be this triangle right here. Now, there's a couple of important things to note about this integral, the first of which is that this is a region above the axis. And so that would usually indicate an area that is positive. But the fact that we are integrating backwards, we are integrating from 0 until negative 1, so we're integrating from right to left, that's going to make that area, which would normally be positive, it's going to make it a negative area. And so my answer here is going to be negative 1/2 times the base, which is 1, times the height, which is 2, and that's going to give me negative 1. So again, because we're integrating the wrong direction from right to left, even though that region is above the axis, that's what makes the answer negative. For g of 2, that's going to equal the integral from 0 to 2 of f of t dt, and so I'll do that in a different color. That's going to be represented by this region right here. So that's a quarter of a circle with radius 2, and so that value is going to be 1/4 of pi times the radius squared, and so that will equal 2 pi. And then finally, g of 5 is going to be the integral from 0 to 5 of f of t dt, and that's going to represent the area from 0 to 5. We already found the area from 0 to 2. That would be pi. Now we're going to find the area from 2 to 5, and so that's going to be represented by this region right here. And because we are integrating the correct direction from left to right, and this region is below the axis, then the value of this area is going to be negative. Now, it's sort of difficult to do this all as one piece, and so what we're going to do is we're going to break this up into two different pieces. I'm going to split this into a triangle and a trapezoid. So if I look just at this triangle first, the area of that triangle will be 1/2 multiplied by the base, which is 1, multiplied by the height, which would be 2. And then I'm going to put a plus sign here. That's okay right now because, remember, I have this minus that's in the front. So that area will still end up being subtracted. And the area of that trapezoid is going to be 1/2. The y values added together. So the y value of this base right here would be 2. plus the y value of the other base, and so that would be 1, multiplied by delta x, and my delta x would be the height of that trapezoid, and so the height of that trapezoid would be 2, and then doing the arithmetic there, we would get pi minus 4 as our answer. Okay, on part B, it's asking me to find all values of x at which g has a relative maximum. So recall from our discussion back in chapter 3 that g has a relative maximum if g prime changes from positive to negative. And so now I need to concern myself with what is the derivative of this function g of x. And because g of x is defined as an integral, we are going to use the second fundamental theorem of calculus. So back up here, g prime of x is going to equal to, we're going to take our upper bound, which is x, and we're going to replace t with that upper bound x. And so that's going to be f of x, and then of course step 2 would be to multiply by the derivative of x, and in that case that's just 1, and so I notice that my derivative g prime of x is equal to f of x. And so I'm looking for now, where does g prime, which is equal to f, go from positive to negative? And notice that this is the graph of f, and I see that it goes from positive to negative, the graph of f does, at the x value of 2. And so that's where the maximum is going to occur on the function g. So I'm going to say here that x equals 2 is a relative maximum of g because g prime, which is equal to f, changes from positive to negative. So please be on the lookout for questions like this. Whenever they give you a function that is defined as an integral, the derivative is going to involve the second fundamental theorem of calculus. On part C, the question is going to ask us to find the absolute minimum value of the function g on the closed interval from -1 to 5. So remember that to find an absolute minimum, we're going to run what's called a candidates test, and our candidates are going to be the critical points and the endpoints of g of x. The critical points are going to come whenever g prime of x, which recall from part B, was equal to f of x, is equal to 0. This is going to happen twice on the closed interval from -1 to 5, at -1 and at positive 2. So x is going to equal -1 and 2. Those are my critical points. And so I'm going to evaluate g of x at -1, at 2, and at 5. Now the nice part about this problem is that we already did all of this back in part A. So -1, g of -1 was -1, g of 2 I believe was pi, and g of 5 was pi minus 4. And so now what we need to do is just determine which of these numbers is the smallest. And we have to do this without a calculator. So notice that pi minus 4 is approximately 3.14 minus 4, which is about -0.86. And I notice that that number is actually bigger than my value of -1. So the absolute minimum value of g, I'm now going to jump into a sentence here in black. The absolute minimum of g is -1, and it occurs at x is equal to -1. So remember a candidates test. Nice part about this problem is that we already did the evaluation of g of x at all of those endpoints and critical points. Finally, in part D of this question, we want to find the x-coordinate of each point of inflection on the graph of g. So it's helpful to draw a little chart over here just to remind ourselves when g has a point of inflection. So I know that g has a point of inflection whenever the graph of g changes from concave up to concave down, or vice versa. This means that the derivative of g prime, would have to change from increasing to decreasing, or vice versa. And recall from earlier in this problem that g prime was equal to f, and we have the graph of f in our possession right here. We just need to find the values where f changes from increasing to decreasing, or vice versa. So I notice a couple of things. First of all, that happens at x equals 2 0. The function changes from increasing to decreasing, and the function changes from decreasing to increasing at x equals to 3. So I have 2 points of inflection here, x equals to 0 and 3. And that reasoning is since g prime, which is equal to f, changes from, and I want to be very specific here, increasing to decreasing, or vice versa. Okay, so a lot of you guys, when drawing this table right here, are used to using f prime, and g double prime, and f double prime. But you need to make sure that you're writing down the letter that matches the function that you're trying to find information about. In this case, we were trying to find a point of inflection on g, and so that helped me sort of puzzle together the fact that I really need to look at increasing, decreasing behavior on g prime, which was equal to f. So be very careful when you're working these problems to use the appropriate letter for things that you've memorized. Okay, on this next example, we're given a function f of x that's defined as an integral and asked to determine the values of x at which the graph of f is decreasing. And so we should remember from earlier chapters that that means that f prime of x needs to be less than 0. So our first objective here is to figure out what f prime of x is. And since the f of x is defined as an integral, to find the derivative, I'm going to use the second fundamental theorem of calculus, which means to take these two t's right here and replace them with the upper bound x. And so this will be x plus 2 multiplied by x minus 3 squared, and then multiplied by the derivative of the upper bound, x, which in this case is just 1, and so I don't really need to write anything there. I'm going to find the critical points by setting this equal to 0, and that's going to give me x is equal to negative 2 and x is equal to positive 3. So using a number line here, I'm going to put f prime on the top and f on the bottom. Negative 2 and positive 3 are my critical points, and I'm going to start testing values in my first derivative. So from this section, if I allow x to be negative 3, then negative 3 plus 2 is negative, and negative 3 minus 3 squared is positive. So that section will be negative, which means that f will be increasing. Decreasing. Let me try that again. Erase and put decreasing. So obviously, first derivative negative means that the function will be decreasing. Sorry about that. And then from negative 2 to 3, I could try 0. So if I plug 0 in for x, 0 plus 2 is positive. 0 minus 3 squared is also positive. So this will be positive and increasing. And if I plug x equals to 4 in, then I'm going to have 4 plus 2, which is positive, and 4 minus 3 squared, which is also positive. And so this will be positive and increasing, which means that the only interval where the graph of f is going to be decreasing is going to be from negative infinity to negative 2. On part B, the question is asking me to write the equation for the line tangent to the graph of f at x equals to 4. So in order to do that, I need to find a point and a slope. So I'm going to first of all find f of 4. That means I'm going to plug 4 into the original function, which is that integral. So the integral from 4 to 4 of t plus 2 times t minus 3 squared dt. And since those bounds are the same, then my value is going to be 0. So that gives me the point 4, 0. For my derivative, I already did this in part A, and so I know that the derivative of that integral is just the x plus 2 times x minus 3 squared, which is found right here. And so evaluating that at x equals to 4, I'm going to get 4 plus 2 multiplied by 4 minus 3 squared, and that's going to equal to 6. And so the equation for my tangent line is going to be y minus my y-coordinate, 0, is equal to my slope multiplied by x minus my x-coordinate, which is 4. Okay, our next question is another old AP free response question. So it gives us a graph of f, and it tells us that g of x is the integral from 1 to x of f of t dt. So in part A, I want to find the value of g of 2 and g of negative 2. So I'm going to start with g of 2. and that would equal to the integral from 1 to 2 of f of t dt. So that's going to be the area of this little tiny triangle right here from 1 to 2. Well, in order to find the area of that, I'm going to need to do 1/2 of the base, which is pretty clearly 1, times the height. Now, the height is not quite as obvious as the base is, but what I do notice is that this y value is -1, this y value right here is 0, and this point, which will help me find my base, is the midpoint of 0 and -1. So that would be 1/2. And notice that my answer needs to be negative since we're integrating the correct direction, and it's a region that's below the x-axis. And so this would equal to -1/4. Now for g of -2, that's going to equal the integral from 1 to -2 of f of t dt. And so that is going to be represented by this little half circle here from 1 until -1. And then from -1 to -2, we're going to have this triangle here. And because we are integrating backwards, these regions are going to take on the opposite sign that you would normally think. So the circle here is really going to be a positive area because we're integrating the wrong way, and this triangle is really going to be a negative area since we're integrating in the wrong direction. So this is going to be a positive circle, so 1/2 pi times the radius squared, minus the area of that triangle, which is going to be 1/2 times the base, which is going to be 1, multiplied by the height, which is 3. And this is a perfectly fine way to leave your answer, since this is a free response question, or you could go ahead and write this as pi over 2 minus 3 over 2. In part B, the question is asking us to find g prime of -3 and g double prime of -3. So we'll start with g prime of -3, and in order to find that, it's probably a good idea to think about what g prime of x is. And so notice up here, my function g of x is the integral from 1 to x of f of t dt. And so in order to take the derivative of that integral, we're going to use second fundamental theorem of calculus. So replace this t with the upper bound, which is x. That's going to give us f of x, and then multiply by the derivative of the upper bound, which would just be 1. And so that means that g prime of x is f of x, and so g prime of -3 is equal to f of -3, and that's going to be represented by the y-coordinate on the graph of f at x equals to -3, which would be right here. Now, once again, just like in part A, the graph doesn't explicitly tell us what that y value is, but it definitely gives us a big hint. The y value here is 1, and the y value here is 3, and that point right here at -3 is the midpoint. And so the midpoint between the y value 1 and the y value 3 would be the y value of 2. Now for g double prime of -3, I notice that g double prime of x must be f prime of x. If the first derivative of g is f, then the second derivative of g is the first derivative of f. And so g double prime of -3 is just going to equal to f prime of -3, and that's going to represent the slope of f at x equals -3. So now we're talking about the slope of this particular line segment, and do that however you see fit, rise over run, or y2 minus y1 over x2 minus x1. Either way, you're going to get an answer of 1. In part C, we're going to try to find the x-coordinate of each point at which the graph of g has a horizontal tangent line, and then we're going to classify each of those points as either a maximum, minimum, or neither. So remember that a horizontal tangent line comes whenever the derivative of a function is equal to 0. And so in this case, we're looking for where g prime of x, which is equal to f of x, is equal to 0. And a quick look at the graph shows that this happens in two different places, at x equals -1 and x equals +1. So starting with the first value of x equals -1, what I notice is that the derivative of g, which is f, is changing from positive to negative. That would create a relative maximum on the graph of g. So x equals -1 is a relative max of g since, or because, g prime equals f changes at that point from positive to negative. Now for the second critical point, or the second point where g has a horizontal tangent line, x equals 1, what I notice is that the derivative, which in this case is f, does not change signs. And whenever the derivative does not change signs, that means that the function, or the point rather, is neither a max nor a min. So I'm going to write here that x equals 1 is neither, since g prime, which is equal to f, does not change signs. So a lot of these concepts that we talked about back in chapter 3 of our textbook about increasing and decreasing and maximums and minimums and points of inflection and concavity, these things are going to reappear now that we're talking about functions that are defined as integrals. Okay, finally we want to find the values of x for which g has a point of inflection. So kind of similar to what we did earlier, g has a point of inflection whenever g goes from concave up to concave down, or vice versa, which means that g prime needs to go from increasing to decreasing, or vice versa. And remember that g prime is equal to f. So where does f go from increasing to decreasing, or vice versa? There are 3 points where that happens, so I want you to take a look and see if you can find them. The first one would be at -2. That one's pretty obvious. The next one would be at 0. That one is the one that our eyes sometimes tend to skip over if we're not careful. And then the third one would be at x equals to 1. So I'm going to write here pretty clearly, x equals -2. Let me do this in black here. X equals -2, 0, and 1. And my justification is since g prime equals to f changes from increasing to decreasing, or vice versa. The next thing we need to talk about in these notes is the average value formula. So if we are asked to find the average value of a function that we have, we're going to use this average value formula, 1 over b minus a, the integral from a to b of f of x dx. Now this is going to be sort of a mental hurdle for us to jump over right now, because now we have 2 formulas that have the word average in them, and so we need to be careful about when to use which one. And again, I would try to emphasize, if you are asked to find the average of a function that you have, a function that you have been given, then you're going to use the average value formula. If not, then you're more than likely going to use the average rate of change formula. So in the first example, it says find the average velocity of a particle if the particle's position is given by s of t is equal to 4t minus 2. And so since they're asking me to find the average velocity and I have not been given velocity, I'm going to use the average rate of change formula, because remember, velocity is the rate of change of position. And so to find the average velocity, in this particular case, we're going to use average rate of change. So this will be s of 10 minus s of 4 divided by 10 minus 4. So if I plug 10 into my function for s of t, then that's going to give me 38, minus if I plug in 4, that's going to give me 14, divided by 6, which is going to end up being 24 divided by 6, or 4. And then let's take a look at the units. S of t is measured in meters, and that's what my numerator was, so that's going to be meters. And then t is measured in seconds, and my denominator was measured in time, and so this will be 4 meters per second. And those units are what I would expect an average velocity to be measured in, and so that's how I know that I have made the right choice here as far as which formula to use. Now in the second example, it says once again, find the average velocity of a particle if the particle's velocity is given. by v of t equals 4t minus 2. And so since they are asking me to find the average of a function that I have, I am going to use the average value formula. So that says 1 over b minus a of the integral from a to b of the function that I want to find the average of, which in this case is v of t. So this will end up being 1 over 6, the integral from 4 to 10, of my velocity function, 4t minus 2 dt. And using the fundamental theorem of calculus here, this will be 1/6. The antiderivative of 4t minus 2 is 2t squared minus 2t, evaluated from 4 to 10. And so this will end up being 1/6 of, I'm just going to do some quick arithmetic here. We're going to have 180 when we plug in the upper bound of 10, so I'll let you verify that. And then minus when I plug in the lower bound, I'm going to get a result of, let's see here, I believe 24. And so the final answer here is going to be 1/6 of 180 minus 24, and so that would be 26. Now I want to take a look at the units before we put the units on the final answer. So I'm going to use my highlighter here, and I'm going to show you here that v of t was measured in meters per second. So this right here is measured in meters per second. When I integrate meters per second, that becomes meters. But then what I do is I divide by 10 minus 4, and 10 and 4 were both values of seconds. And so this meters right here of this integral becomes meters per second once again. And so that's again a measurement that you would expect for an average velocity. So once again, just so that we're clear, this v of t is measured in meters per second. When I integrate, it becomes meters, but then when I divide again, that becomes meters per second. And so that's how I knew I used the correct formula, is because the units checked out at the end. Once again, I used the average value formula because I was asked to find the average of a function that I had. They asked me for average velocity. I was given velocity, and so that's why I used the average value formula. All right, the next question I'll let you read for yourself, but what I want you to notice is that the function that they've given us in this problem represents the speed of traffic on a certain freeway exit, and what they are asking us to find on this problem is the average speed. And so because they are asking us to find the average of a function that we were given, this is going to be the average value formula. So 1 over b minus a, and notice that in this problem we're trying to find the speed between 1 and 4 p.m., and that t is measured as the number of hours past noon. And so that would be 1 and 4 as my bounds of integration. So 1 over 4 minus 1, the integral from 1 to 4 of s of t dt. This formula will give me the average speed. And so using your calculator to evaluate this, what you're going to end up getting is 65.5. And I want to make a quick discussion on the units just real quick. Notice that s of t was measured in kilometers per hour. So this right here is kilometers per hour. When I integrate that function, the per hour just drops off. So this integral now represents kilometers. But what I did here was I divided by hours, and so that means that my final unit is kilometers per hour, and that is something that we would expect average speed to be measured in. And so once again, that sort of just helps me confirm that I've used the correct formula. Okay, in our last example here, we are given a table. It says that water is flowing into the tank over a 24-hour period. The rate, which is a very important word in this question, at which water is flowing into the tank at various times is measured, and the results are given in the table. The tank contains 150 gallons of water when t is equal to 0. So it's a very important fact in this particular question. So to estimate the number of gallons of water in the tank at the end of 24 hours, I'm going to use the idea that in order to get an amount, if I'm given a rate, I need to integrate. And so the number of gallons of water in the tank is going to be represented by, first of all, the initial value of the amount of water in the tank, and so that would be 150, plus the integral from 0 until 24 of this rate at which the water is flowing in, r of t dt. And so this is going to be approximately 150. And now I'm going to do what the problem says to do, which is to use a midpoint Riemann sum with 3 equal subintervals. And so remember, in order to use a midpoint Riemann sum, I've got to be able to take something from the middle. So this is going to be my first subinterval from 0 to 8. My next subinterval will be from 8 to 16. And my third subinterval will be from 16 to 24. And I want to take all of the numbers that are in the middle. So that would be the 8.8, that would be the 9.2, and that would be the 8.1. So this is going to be 8.8. Let me just go ahead and do that in black here. 8.8 multiplied by the width of that subinterval. And from that subinterval, I get that the width is 8. Plus the next subinterval, which is going to be the 9.2 from the middle, multiplied by 8. And then finally, plus 8.1 multiplied by the width of the subinterval, which is 8. And the unit on this particular answer is going to be gallons. I'm going to leave the answer in that form since this is a free response question, and I'm certainly more than allowed to do that. Okay, on the next problem, it's asking me to basically do the same thing here, except this time I'm going to be using a trapezoidal sum with 3 subintervals, and so the subintervals are going to look exactly the same here when we do this, but instead we're going to be doing a trapezoid. And so I'm going to start with my 150, which was my initial value, integral from 0 to 24 of r of t dt. So that's my needed amount given a rate, then integrate. So this is going to be 150 plus, for a trapezoid, I know that that's going to be 1/2 the y values added together, so 8 plus 9.3 for my first subinterval, multiplied by the width of that subinterval, which is going to be 8. For the second subinterval, so that would be the one from 8 until 16 here, we're going to do the same thing. 1/2 of the y values added together, 9.3 plus 8.9, multiplied by the width of that subinterval, which is again 8. And then finally, for the last subinterval from 16 to 24, we're going to say 1/2 of the y values, 8.9 plus 6.7 added together, multiplied by the width of that subinterval, which is 8. And the unit on this particular answer is going to be gallons. Okay, part C is essentially asking us to do the same thing as parts A and B, but this time it gives us a function that they says models the rate at which the water is flowing into the tank. So this W of t is basically like a nice function model for the table that we were given in this particular problem. So that's what they're wanting us to use on this particular question. So once again, I'm going to have my initial value of number of gallons of water in the tank, plus the integral from 0 to 24 of W of t dt, since that's representing my rate. Now I'm just going to use the calculator to evaluate this, even though we could do this problem by hand, and this is going to give us 357.36 gallons. In part D, it says use the model given in C, which remember represents the rate at which water is flowing into the tank, to find the average rate of water flow over the 24-hour period. So this is going to be the average value formula because they are asking for the average of a function that we have in our hand. This function right here represents the rate of water flow. And so in order to find the average, we're going to use the average rate of change. So 1 over b minus a, the integral from a to b of w of t dt. And the value of this is going to give me the average value. This would not be average rate of change because that wouldn't give me the right units and it just wouldn't be correct. We have the function w of t in our hands. It was given to us. We were given the rate. And so in order to find the average rate, we're going to integrate that and then divide by b minus a. So just typing this into the calculator just real quick to get the answer. And then we will be on our way. And I got 8.64. 8.64. And this would be measured in gallons per hour. And so let's think about that for just 1 second to make sure that we're correct. W of t was measured in gallons per hour, but when we integrate gallons per hour, this whole thing now becomes gallons, but this right here makes it back to gallons per hour, and so that's just a confirmation that I have indeed used the correct formula. Okay, that'll do it for the second fundamental theorem of calculus and the average value formula. If you guys have any questions, then please feel free to let me know.